Hi, this is Mark Overmeyer, and I'm going to go over the construction, feasibility, and performance of the electrical prototype. The prototype circuit is based on the LTC3105 microchip. The example circuit, shown here, is very close to the actual circuit used in the prototype. The chip takes the incoming voltage coming from our generator, stores it in the capacitor until enough is stored to deliver it at the Vout section here, at the voltage that we select using the voltage divider. This makes it very flexible for our needs. Shown here is a breadboard of the actual circuit. This is the LTC3105. This is the voltage divider. This is the storage capacitor. And this is the USB output. Here's a side view of the prototype circuit. To save money, I hand soldered the LTC3105, shown here, to a breakout board shown here. A quick comment on size. The circuit appears pretty small when compared to a quarter. However, all of the components here are the larger versions I used for prototyping because they were cheaper and easier to work with. From the capacitors to resistors, there are components available that are fractions of the size that we can use for the final design. Also, a breakout board would not be required because the LTC3105 would just be put directly on a printed circuit board. Now let's test the prototype under a few usage scenarios. By transferring a circuit to a larger breadboard, I was able to connect it to an oscilloscope with two inputs and a function generator. Here you can see the successful conversion of 3.5 volts in yellow to the usable 5 volts in blue. Next we'll try the positive portion of a 1 Hz sinusoid. Again, success. The next input is a random blip of below 4 volts. You can see most of them create a nice square wave at the usable 5 volts. Even as the input voltage decays, 5 volts is maintained. For the final test, we'll supply 3.5 volts while connected to my iPod. When I plug it in, notice that the iPod starts up and starts charging.
In the world of tomorrow, we will all be working with huge teams of people from around the globe on projects which will optimize our individual core competencies. This presentation will focus on one group in an in-class team project which discovered that communication can be a key driver in the integration and coordination of large mass collaborations, and that valuable lessons can be learned from the painful process of miscommunication. This course, ME6102, Designing Open Engineering Systems at Georgia Tech, covers a wide variety of topics. One of the ideas woven throughout the course is the idea that the combination of the forming global value network, the flattening of the world, and the proper application of open innovation will drive future teamwork toward global mass collaboration. Understanding the system is key to being a competent, competitive engineer in the future. With this in mind, the class project was an application of these ideas. The entire class was tasked with the design of a product, hydroelectric footwear in this case, and expected to self-organize and in the end create a prototype product, a report, and a presentation. This workspace which was suggested was that of Wigio. Wigio is a free online workspace and enables people to interact with a large number of group members through web meetings, forum posts, and file sharing. The original task of the team that we formed was to help integrate the requirements into the design. In this process, we noticed that the main problem was that of communication throughout the team. Our original work was either ignored or reproduced. However, instead of being frustrated, we were curious and began to explore this issue. It turns out that in these types of self-structured teams, there is a direct link between the structure of a team and the type of communication that is used. This link goes both ways, as the communication drives the shape and the structure of the team. Not enough structure in a team can lead to chaos, but too much structure can leave everyone drowning in red tape. Large groups, such as those in a mass collaborative setting, don't need lots of rules and structure to be productive together. In fact, a very small number of interaction rules can lead to very beautiful and incredibly complex behavior. Bird flocking, for example, is driven by a very small number of rules, but results in amazing behavior called emergence. These concepts must be integrated into the teams of the future to provide adaptable and effective utilization of mass collaboration teams. However, us humans are a bit more complex than birds and require some level of communication in order to work collaboratively. Communication has been greatly enhanced by tools such as Wigio. Technology now connects us globally, enabling communication across wide distances both culturally and physically. This 30% rendering of the Internet in 2003 shows just how complex this communication network really is. Utilization of these types of technology-driven communication devices are essential if a team is to perform as a group and produce useful, well-coordinated work. However, just as with structure, too much communication can cause an overload. Given these ideas, an initial organization was based upon the traditional Paul and Beth design methodology, with subgroups taking on parts of the design. The task part of the project came from our professor in the course. Requirements for the product were developed in subgroups as well as collaboratively in the Wigio workspace. There were teams formed for the design analysis and prototyping as well as for the work report and the business case. It should be noted that for the most part there were people in multiple teams, but it is the intergroup communication that we are interested in here. How did ideas pass across team boundaries and grow as they were worked on by various participants? An idealized view of the initial structure shows how the 6 main groups coordinated through a common space, Wigio in this case, and how the workflow is in a logical direction as indicated by the dotted line. In reality, however, this was not the structure that formed, and a more realistic view of the group structure is shown here. Most of the work flowed toward the work report group, as that was the deliverable for the course. The design team was quite large, and the dark lines around all of the groups are intended to indicate that there was very little external communication from the groups once the project started. The exception to this is that of the developing the requirements. This started in a subgroup and was moved out into the collaborative space as more people contributed to it. However, in general, there was very little intergroup communication that was visible to the entire team. Communication can be divided into 2 different categories: direct communication and indirect communication. Direct communication fell into 2 extremes. Meetings, online and on the phone, took place during the initial phases of the project. However, since most of the team was distributed, it was difficult to get everyone to meet in a synchronous fashion. Another method of gathering information is to poll people through Wigio. This allowed for asynchronous input but had very low fidelity in the information which was received. The predominant form of intergroup communication occurred through the main page of Wigio, which was a rolling forum website where users could post threads with various topics. There were a total of 113 total posts to the Wigio main page. The requirement integration development progressed quite nicely, with many contributors posting revisions to the file. There was some confusion with name changes, which happened a number of times, but in general the requirement development progressed as a result of the mass collaboration. It even spawned some concept generation just before its final revision. However, this concept generation didn't go anywhere, and this is where we begin to see some of the problems in communication that we had as a result of the structure. There were a large number of dead-end files. These files that many people put a large amount of work into but were not continued or pulled forward. Some of the work was repeated elsewhere in the group, and some of it was integrated into teams. However, not only are dead files very inefficient, but they were very demoralizing for people who put a large amount of effort into their work. Having said all of this, it is an opportunity to learn and improve, and it is important to note that there are only small changes necessary to optimize the system. In reality, the group functioned in a method known as concurrent engineering. This means that the manufacturing and design occur at the same time. In our case, though, this meant that the groups were all working on the project at the same time. This is an excellent way to fully utilize teams, but can lead to confusion and requires extra communication. This type of structure is very common in the field of open source software. There are a number of modules which are being developed at the same time. Then, they are all bundled together and shipped out to the customer. The customer provides feedback or changes things themselves, and the cycle continues. Ideas or updates which do not make it into the last revision are not lost but can make it into the next revision. Furthermore, this feedback improves the vertical integration of the entire design team. Another example of feedback is the internal review. Only when the ideas meet certain standards are they let out the door. A harmonic laser, for example, works exactly in this way. Ideas, or power, flows back and forth in the laser medium. As the medium becomes in sync, equivalent to everyone agreeing in the group, the energy becomes high and the light escapes through the partial mirror. Until the light gets intense enough, it is bounced back through the lazy media, sending off another cascade, similar to multiple design revisions. The first solution posed to solve some of the problems we had as a group is to add a feedback loop just before the goalposts. This would allow feedback, as all teams would see that the others have been working on and can use that as a starting point. The design cycle time would decrease dramatically, and this type of structure would be much more robust to things like customer or market changes. The other solution has much more to do with the way that groups communicate with each other. In our bodies, our cells differentiate the work that they do inside to that which is happening outside their cells through active semi-permeable membranes. These membranes are very complex and allow messages to be passed to other cells, but do not allow the noise of the surrounding communication to interfere with their internal workings. While our solution was to block most of the communication from each other, perhaps a better idea would be to increase the porosity of those walls. By reducing the inter-team barriers, information can be gleaned by various groups simply by floating in and out of the organizational structure of these subgroups. Core team members could work on the project all the while gaining information by observing what is happening in other groups. There were a number of lessons learned during this work. First, that there is an optimal amount and quality of communication, which is closely coupled to the structure that emerges in the group. This structure and communication need to enhance productive collaboration, not detract from it. And finally, the information and value produced need to be in a usable form as possible. Things such as common form can make a huge difference.
Thanks for staying with us during the video, and with this I will conclude our presentation. We started with an introduction to our project and addressed its relation to many of the topics we covered in class. We then talked about the applicability of mass collaboration and provided you with a gap analysis, the business case development, and market research plans. We then went into the project and customer requirements, and then into the footwear's conceptual design. Afterwards, we provided you with a complete system analysis including stress and fatigue, and then we took you to our working mechanical and electrical prototypes. As a result of seeing our development from start to finish, we hope you have a thorough understanding of our project and the work we did along the way. If you have any questions whatsoever, please send them to the email shown on the screen, and we will do our best to address your questions as soon as possible. Again, on behalf of the Hydroelectric Footwear team, we thank you for watching.